In the middle of the 20th century, Scotland experienced an energy revolution. From the 1920s until the 1970s, thousands of men laboured to build huge dams and power plants, enabling the production of renewable hydroelectricity on a grand scale. Harnessing this power from the glens was difficult, dangerous work, but the energy created supplies countless homes and businesses across Scotland to this day. Now, half a century on, this small nation is bearing witness to another vast engineering triumph. But this time, the power is coming not from water, but from wind.
Part of SSE is Scottish Hydro. It's part of the heritage, it's part of the DNA of the company. The wind has allowed us to reawaken that heritage and bring it up to date.
We've achieved 1,400 megawatts presently, more than what was achieved in the 50s and 60s from the whole hydro portfolio that we built in those days. And we'll ramp that up to 4,000 megawatts by 2025. The overall capital cost of that onshore wind farm programme will be about £6 billion.
SSE currently has 700 wind towers in operation around the country, from Sutherland to South Ayrshire. To more than double current capacity in little over a decade is a highly ambitious target. Achieving it will require the addition of another 1,300 turbines in sites spread across the UK, from the Shetland Isles to Essex.
Onshore wind is the cheapest form of low-carbon electricity and renewable energy. It's cheaper than nuclear, it's cheaper than offshore wind, it's cheaper than hydro. Therefore, it is the most economic way of society meeting its needs to clean up its energy supply. And that will remain the case. So it is entirely the right thing to do for any country, be it Scotland or anywhere else, to maximise the potential for its onshore wind resources.
Being blessed with a strong natural wind resource is one thing, but wind turbines don't just grow on hills. Each wind farm demands years of planning just to get to the construction phase. But long before that, the process begins with the identification of a suitable site.
We review the available land, in terms of what landowners own individual pockets of land, and we review that against what information is publicly available for them. In terms of do they have any environmental designations. We review the wind resource available for each site, and from that we make a decision on whether a site should be taken forward or not into development.
We'll identify an area that we would be interested in. From there, we would speak to the landowner, see if they were interested. If they were interested, then the next stage would be to put it through an early feasibility type stage.
The planning team must think about more than just a site's future prospects. Its past and present inhabitants are also given careful consideration, thanks to archaeological and ecological surveys.
Once a site's handed to me from the site feasibility team, we'll commission ornithologists to go out and carry out the first years of ornithology surveys. Once we establish that the ornithology constraints on the site aren't of such a magnitude that we wouldn't want to progress the site any further, we'll then commence preparation of the scoping report. That's basically to give us the detail behind the environmental impact assessment, so it will determine what additional surveys, assessments, analysis that we need to carry out and include within that impact assessment.
Our involvement in a project like this would start with a desk-based assessment where we would examine old maps and air photographs, assess where things had been found in the past. That would provide us with background information to go out and do a field survey, assess whether they still exist, their condition and their vulnerability to the development. Once that task has been completed, we will compile a report which will be sent to the council and mitigation measures can be put in place.
Once the All the surveys and assessments are carried out and we've refined the design. The application will be submitted. Hopefully we obtain planning consent. Once consent's granted, the project is then handed over to the construction team.
It is only now that detailed ground investigations can begin.
From desktop studies and the information that we've been given before we come to site and from geological records, we would tend to know what the ground is made up of, how much soft material overlays the rock, the type of rock. We then come along, we have specific locations where we carry out the investigation, trying to confirm the records, whether they're the same as what we expect or whether there's any changes across the site which might affect the location of the turbine, it might affect the foundation of the turbine, and also any problems which might come up in the construction.
The information gathered at this stage plays a significant part in determining the layout of the proposed wind farm. But whatever complicating factors are thrown at the planners, it remains vital that the final site is designed to maximise the available wind.
Initially, it's really laid out based on resource, so it's based on how much wind you can get from each turbine location.
We need to consider issues such as shear and inflow and turbulence, which are all factors that the wind has, depending on the topography, proximity to trees, as well as the wind direction. Does it get channeled up a valley? Does it come over a col? All of those then to be considered by a resource assessment team and helping us define a layout.
We'd measure the wind speed on a site for a minimum of 1 year, ideally 2 or more, and then use that to model the actual flow across the whole of the site, taking into account things like the terrain features like trees, forests, and then the orography. And then we run that through some other models to capture how the wind flows through the site when the turbines are operational, and to capture the weight losses that you get from the turbines generating.
One important consideration for the planning team is how each turbine's position relates to those of its neighbours. Each tower must be situated 5 to 6 rotor diameters from the next. This separation is necessary because as air passes over a turbine, the blades create turbulence. Keeping an appropriate distance between the towers allows the turbulence to abate, preventing disrupted air from reaching the next turbine and reducing its energy yield.
Once you've got your spacing of your turbines, you then need to look at how that works on the landscape you have and the topography. As wind approaches the landscape, if it hits a hill and is pushed up the side of that hill, then the wind may create mechanical stresses which are bad for the operational performance of the machine. So we need to then look at whether we can site a turbine away from a cliff edge or away from a steep slope, and still maintain the grid spacing from the next turbine and maintain the spacing from the environmental constraints.
Look at the plan view, John.
When it comes to the design meeting, they would sit with all the other parties who are involved, the ecologists, etc., the ornithologists, and through their information you can refine the design. You can look at how it's going to be visually in the 3D form with all the spatial data put into the one place. There would be concerns if you were building turbines that spoiled a view with Edinburgh Castle, for example. So you could then say, well, I'll take the castle, and you could run a reverse visibility on it and say, well, what is visible from the castle and what's not, so you know that you wouldn't want to encroach that space.
Given the concerns as well, I don't think we need to put any turbines in a position like that could cause us problems in the future. We'll say where we want to put the turbines from a resource perspective, and then civil engineering will say, well, you can't build it there, or it's going to be very difficult to build it there. Can you move it here? So then we'd have another look and go, yeah, okay, we can move it this way a bit. And then the visual guys will come in and go, wow, that looks terrible. Can you move it down the hill? So then, it ends up being a big compromise, but essentially trying to balance all these different aspects to produce the best layout that you can.
This site shouldn't just be looking good, and it shouldn't just be avoiding the environmental constraints, but it needs to work. It needs to be constructible from day one.
Once a site's layout has reached final agreement, all planning requirements have been met, and official consent has been granted, the real work can begin, starting with site clearance.
People who are passing the site and see wide areas of felled trees. The areas that are being taken down are non-native, very densely planted, with fairly low ecological value. And as part of the habitat management plan for this site, they're being replaced with high-quality moorland and heathland, which are sort of target conservation habitats.
Preparing the internal terrain of a wind farm for its family of turbines is headache enough. But for each site, thought must also be given to the surrounding infrastructure and the feasibility of delivering large turbine components via local access routes.
Some of the major civil engineering constraints that we faced on projects are definitely one-offs. For our Griffin wind farm, we had to lower the road level beneath an operational railway line, and that was a major undertaking at the Ladywell Bridge. That was approximately £2 million worth of work and took a number of months to deliver, and without it the wind farm itself would not have been possible. At our Keedby site at the moment, we've just completed the installation of a £5 million bridge that needs to cross 2 land drains, a canal, a network railway line and a high pressure gas main, and that in itself is a major civil engineering project, irrespective of the fact there's a wind farm to be attached to the back of it.
Such are the complexities of wind farm logistics that challenges can emerge not just on the ground but also from the skies. The largest wind farm in SSE's portfolio had to overcome a unique problem to prevent the site from sending out the wrong signals.
It was identified early in the development phase that there would be an impact on the local primary radar station adjacent to Clyde Wind Farm from the turbines. The turbine blades have a similar effect on air traffic controllers' screens as an aircraft does. So what we have to do is remove the wind turbines by cutting out the airspace from one radar and infilling it from another radar by developing this radar site in Cumbernauld.
Before any civil construction works can commence, every wind farm site has to be marked out with painstaking accuracy.
90% of the setting out is GPS. Got a base station at the top of the hill that transmits mathematical corrections to the rover. We walk about, we've got all the information uploaded into the rover. So it involves a lot of walking, a lot of bashing in pegs, walking about, especially we're the first guys in, over the hill, carry the pegs in, start marking it out, and then everybody else comes up once the job's done.
With site marking in place, civil works can begin. This entails a lot of big lorries with big loads, as the site's internal roads and infrastructure are gradually created. To minimize the amount of heavy traffic on local public roads, the stone required for the civil works is hewn from on-site borrow pits.
There's going to be more than 50,000 cube getting removed from this borrow pit, but the final total, I suppose, depends on the amount of peat and excavation that has to be done on the way up the hillside. The explosives nowadays are very stable. It's non-electric connectors and debts that we're using. It's a plastic tube which is lined with a very fine layer of explosive. It's a lot safer than the electric systems of years gone by. Today we're using approximately 3 tonnes of explosive, and that will produce around about 7,000 cube of rock. Ollie to the sentries, just checking we're still all clear. Firing in 10 seconds.
The on-site roads, which must bear the arrival of massive wind turbine components, have to be formed upon challenging terrain. And it's another energy source that can pose the biggest problem.
It's been pretty good up till now. We're going into the more challenging areas now where there's deep peat, and that can cause a few different scenarios, if you see what I mean, because the peat will run towards you. So you can just place rock beside it, hold it back, and generally just project your road right through that.
Staying on schedule in such environments is challenging enough in the summer months, but when winter sets in, its onslaught can see morale plummet as fast as the temperature gauge.
It's been tough with the weather. It's been freezing. It's freezing today. Gales, it's been pretty tough to deal with, but we get there.
Given the lengthy duration of each wind farm's development, every project experiences its share of awful conditions. But thanks to the countless hardy souls on site, work continues come what may, because the first delivery of turbine components is not far away. Many of these components will come from SSE's own factory in Machrihanish on the west coast of Scotland.
The way it works is if you've got an order to place, we'll place it with Windtowers in Machrihanish for the supply manufacturing of our Windtowers. It keeps the supply chain in Scotland. It keeps jobs in Scotland. You know, in Campbelltown's being a small area, it's all local people we employ. It's a supply chain partnership. That means that the steel work that we get coming through Windtowers doors, we can trace it back to its origins. We know it's certificated. We know we're getting a good product at the end of the production line, which gives SSE a lot of comfort.
The steel plate's delivered here, it's then moved to the roller. It's rolled into a conical shape. It's moved from there to the sub-arc machine on the long seam, which is sub-arc. It's then moved to the blaster, which does the weld prep edges. It's moved from there up onto the tower section. It's then sub-arced, then moved from there to a QC department, final visual. Some UT reports are done on it, and then it's moved out the door to paint.
Basically, this is the surface treatment. In here we've got the blast hole, where basically we take off the rust and make the tower silver and give it a profile. It goes from here into here, where we metallise it. Different towers at different specs. Basically, it metallises a corrosion protection. Then we wheel it up, ready for painting. The boys scrape off the excess shot, and then it goes onwards to the last stage, the third stage of the process, where it gets painted, and then from there, out the door. And that's the surface treatment.
The cans arrive fully fabricated and painted. It arrives in our department here, the final fit department, to be fitted out with all internal equipment from fall arresters, any emergency equipment, lifts, ladders, all the electrical fittings and generators will be fitted by the teams that work in here. Once that's done, the whole interior will be washed out, interior and exterior will be washed out to high standard, sealed and then shipped to site for the customer.
Before any turbines can be built on the site, sturdy foundations must be laid to bear these huge structures.
To allow a turbine to be erected, you have to prepare the ground, you have to install the foundation, and you have to ensure that the ground conditions are sufficient, they are firm enough to place the concrete, quite a large volume of concrete, and in addition to that, steelwork.
Soil investigation surveys will give a good indication of what the ground conditions are going to be, but you'll not know until you actually dig out the hole what you're going to encounter. Water courses, peat pipes, a variety of different things. It's the soft sites you need to worry about.
Basically what we're doing today is just trying to dig down and get solid rock, you know, unbroken rock that can form part of the turbine base, which has proven to be a bit difficult.
Once the challenge of identifying a natural rock base has been met, the man-made foundation can be constructed on top.
Foundation will be approximately 350 cubic metres of concrete, so that gives you about 760 tonnes of concrete with about approximately another 1,000 tonnes of material ballast over the top of it. So you've got approximately 250 tonnes being held down by 1,700 tonnes of foundation. So it's going nowhere.
Once all that's placed, you backfill it, you place an earthing mat around it, and once it's all complete with a hard standing area for the crane to lay down on, then you can physically start the erection process.
There are a few finishing touches before the hard standing area is handed over to the site subcontractor, in readiness for the turbines to be erected.
Once the civil
contractor has completed the foundation and the hard stands. Ourselves, the crane company and the transport company come to inspect the foundation. We inspect the hard stand area to make sure it's of sufficient size and it's correct to the design drawings. Once we're happy with that, we then take acceptance of the hard stand, take it over, it becomes our area.
With the foundations ready to receive their towering occupants, there remains the small matter of transporting the turbines to the site.
One of the major issues is the turbine blades themselves are 49 metres in length, which is half the length of a rugby pitch, so they're sizable objects. We've had to make some fairly major modifications to the public roads off-site in order to allow these to be delivered, and the roads on-site have to be designed to cope with these long and, in other cases, heavy loads.
Each turbine will be over 120 metres in height. To stand each one upright, it will require the help of not one, but 2 cranes.
The smaller crane actually builds the bigger crane, then assists the large crane to erect the turbine.
The whole process is quite quick. With the tower sections, it can be as quick as an hour for each tower section, an hour and a half for the nacelle, and the rotor assembly itself takes around about 4 hours to put together and about an hour to fly. So in a day, with perfect conditions and with no problems, you can build a turbine.
When we're erecting the tower, the large crane will lift one end and the smaller crane will lift the other end. And we call it what you call a tandem lift. We lift it up, and then once it's clear of the ground, the large crane then proceeds to lift, and the smaller crane starts to lower off to release its weight until we have the tower section vertical. Then we release the small crane from the section, move the section into position, land it into position, and then we just continue with that with the other 2 tower sections.
It may sound straightforward, but pinpoint precision is required to stack the tower safely and accurately.
From that stage, the nacelle, which houses the gearbox and the generator, we then lift that into position, but we have to make sure that the weather conditions are good for that because the nacelle actually weighs 87 tonnes, so we have to have pretty perfect conditions for that.
Last, but very far from least, is the rotor assembly.
The rotor assembly is the largest item that we lift. It covers a wide span. You have 45 metre long blades. We assemble the blades into the rotor with the rotor lying on its back on the elephant's foot, and we can leave it left in that position so long as we tie the blades down.
Edging the hulking blades into place is challenge enough, but once the blade assembly is complete, there is still the considerable task of hoisting it into place on top of the tower. The powerful winds that make these sites ideal locations for wind farms also make them a very difficult place to build them.
Maximum lift and wind speed is gusting to 9 metres a second. If we're in that parameter, we have to decide to maybe not lift above a mid-tower section. We look at weather forecasts on a very regular basis. We also have to pick up the wind speeds from the crane anemometer. That dictates how the crane driver will operate. You've got 60 tonnes nearly of weight there, and it's designed to actually catch the wind. That's the design of the blades, and to lift it in any kind of adverse weather condition is extremely dangerous.
When you've been working on a wind farm for a length of period of time, you get to know the wind patterns, and you can pick a wind pattern where you know that you're definitely going to get this rotor up. If there's any doubt at all that you think that the wind is going to get up too high for it to lift the rotor, then you don't lift it, it stays on the ground.
Once you pick up the rotor assembly, that's it. It's got to be assembled. It's impossible to fit the blade clamp back on the blade with the tailing crane to drop the assembly down again. The ideal world is that we have no wind or 5 metres a second, but we're on top of a big hillside in Scotland. We'll always have wind.
The installation of this cumbersome structure is a masterclass in crane coordination.
Once the rotor's actually flown, it takes 45 minutes to take up to the top, and all the time it is governed by the crane management, guide ropes, and a crew at the bottom which is in contact all the time with the crew at the top, who then manage the actual meeting of the turbine blades with the actual nacelle. It's so accurate, it's done to millimetres. Once it gets closer, the wind has less effect on it because it's closer to the actual crane and closer to the nacelle. The biggest part is lifting from the base to the top.
People misunderstand the time frame for building turbines. Sometimes we can get up to a nacelle level, the rotor is assembled, and we're waiting a week for the weather to calm down enough to be able to pick that rotor assembly up.
Now, safety is paramount to the success of the project, so we won't risk the safety of any individual on the site just because we can get maybe a turbine up early with based on the fractions of wind, so we'd rather deliver the project safely than have an issue with somebody's life.
The purpose of a wind turbine is simple, but there's some complex, clever engineering at work inside. The blades receive energy from the wind as it blows over them, translating it into rotational energy. This is transferred along the main bearing within the nacelle, spinning it and putting torque into the gearbox, which turns a shaft in the generator. As this happens, magnets are being rotated through an electrical field, creating electrical energy. But as wind characteristics are not constant, some flexibility is required. Blades need to be able to alter their pitch depending on the wind's speed and bearing, so they're designed to rotate around their axis, while the machine itself can also follow the wind's direction.
The turbines themselves, they take quite a hammering from the weather in all weather conditions. They are certainly a great feat of engineering and a fantastic bit of kit to be working in.
Throughout a wind farm's lifetime, the involvement and well-being of nearby communities is of paramount importance. Being a near neighbour has its benefits: job opportunities, local environmental and infrastructure improvements, not to mention the clean energy produced. But there are also windfalls to be shared. SSE has already set aside over £11 million for community investment funds to help support educational schemes, public amenities and volunteer organisations.
It's recognition that local communities are hosting the wind farm in their area. It's to sort of recognise the fact that there will be some disruption during the construction phase, but also to give them a much longer sort of long-term investment fund so that they can plan what they want to use the funds for and to do some good in the community as well. And they're looking after our wind farm for us, if you like, in the local area, and it's nice to give something back.
Thanks to their sheer dedication, and in spite of the difficult challenges, countless individuals have helped to make these vast feats of engineering an outstanding and ongoing Scottish success story. Across the nation, hundreds of these steel titans are now turning quietly, day and night, and each turn of a turbine blade contributes to a larger revolution, shifting the production of power towards a renewable future.
There's a sense of pride
the great achievement that the SSE team have done in developing and building this project. So the professionalism and skill of the team is amazing, and as a humble accountant I'm amazed at the scale of the operation, the challenges and the engineering and craft skills that have been deployed here.
It's absolutely fantastic being involved in this programme, and it's fantastic working with a lot of really dedicated and professional people.
The team and the workers involved in the construction wind farm have been tremendous. I've got the utmost respect for them. The varying weather conditions, the difficulties associated with the various elements and interfaces in the construction has proven to be a huge challenge, and they have all overcome it.
We can't go on misusing and abusing the planet as we've been doing. We have to move to renewable forms of energy, and Scotland, I think, should lead the way in that. We shouldn't just follow behind, we should actually lead the way, because we've got some of the great resources.
Scotland can absolutely and will meet its own energy consumption from renewable sources within the next 5 to 10 years. And Scotland absolutely has the potential to export clean energy. Scotland is uniquely blessed with the right geography and the right engineering skills and heritage to be a renewable powerhouse.
Renewable energy has always been our tradition. It's been at the heart of everything that we have done. In the past, the engineers, our forebears, built their hydroelectric dams from 1920 to about 1970. So over a 50-year period, they created over 100 dams, 1,000 megawatts of power from the glens. They became a tradition, a legend of their time within hydroelectric. We're sitting here with new engineers, new challenges, looking to put in almost 4 to 5 times as much power for over a 20-year lifespan. It's a huge engineering challenge for our engineers, and will create heroes of a new generation.